Well, good afternoon. Welcome back to Chemistry 401. We have yet another lecture for you today. I do have an announcement, and that is, if you're interested in medical school or medical research, there is a collaboration for undergraduate research between Sacramento City College and the UC Davis Health System. It's actually very exciting. Our students have already started in it for the first round, and this will be the second round on Friday, March 15th, which is this Friday, 11 to 12:30 at main campus. They're going to have an information session. Lillard Hall, 205. If you're interested, it's a new program, but the feedback we're getting, and this is organized largely by Professor Bin Dow, another one of our undergraduate researchers at the main campus. And the feedback we're getting is that the students are doing really well. They really like our students, and the students are getting really good experiences. If you go to the information session, you're supposed to get to hear from students who are in the program now about what they're doing. So, I thought it was a fabulous opportunity. So I thought I'd bring it to your attention. I have a flyer for it here too. And I will start on this side of the room, passing it around. Take a look. Now, homework. Homework number 3 is due on Wednesday. It is due by 12:30. There will be no exceptions. That's not a surprise at all. What I'm seeing is a lot of people who are working with their Ka and their Kb values. And in particular, I'm going to just take a minute here and go over and make sure you should be able to, by the end of this homework that you turn in on Wednesday, calculate the Ka or the Kb value for almost anything. And that will be a useful skill. There's a couple things you need to know, and by way of example, let's see. I'll take the compound sodium acetate, and I can ask you a number of questions about this compound. The first question would be, if you dissolve sodium acetate in solution, will the pH be greater than, less than, or equal to 7? Can anybody tell me the answer to that? David? Less than? Less than 7 would indicate that it would be that one of these is an acid, right? And it turns out that one of these is an acid. Let's break it down and decide what kinds of acids they are and what kinds of bases. When you look at positive ions, you should think that is most likely to be an acid. And positive ion here is sodium. Sodium is, so the first, or the short answer would be it's inert, it's a spectator. We never care about it. It does not affect the pH. The slightly longer answer, which I don't know if it's worth knowing or not, is that if this is an acid and you take a hydrogen away from it, which is what you do to acids to get conjugate bases, there are no hydrogens to take away from it, but the conjugate base would be the hydride ion, which is a strong base. Anyway, what I remember is that sodium is an inert acid. It is a spectator. I cannot think of a single instance where sodium does anything of interest chemically except dissolve and leave you with something interesting. So this is going to be an inert acid, which means it doesn't affect the pH. Now let's talk about this, though. So, and David, does that make sense? About the, okay. Now let's look at this. This is acetate and negative ions. Your first thought for negative ions is they're going to be bases. It's true that if you have something like bicarbonate, while it is a base, it can also be an acid too, and your hint that it can still be an acid is the H in the front. This can be an acid or a base. This one, only a base. And it is the acetate, and so it is a base. And so now we have to decide whether it's an inert base, a weak base, or a strong base. Can anybody tell me what kind of base it is? It is a weak base. And we may or may not know that, but here's the process for finding it out. If this is negative and it's a base, then I can find its conjugate acid. Its conjugate acid has an additional H plus, CH3COOH. Now, ironically, although I'm not sure if I'm using ironically correct there or not, if you look on your conversion equation sheet, it actually has this version of acetic acid. These two are the same, and by the time you get to your exam, and we've been talking about this, and another example of, maybe you find this, maybe you don't, of me taking feedback, on your second exam, I'm going to have not 15 pages of conversion equation sheets, but just 1 or 2 with all the key values on it. And for acetic acid, it will say CH3COOH, so it will be clear. Because it's not now, and I apologize. Anyway, so, uh-oh.
That's the first time it says ever.
Well, I don't need it yet, but I will at some point. Speaking of not being clear, that's what I'm hoping. No. Those of you who were in lab this morning, it's just one of those days. Oh. Let's see, so that is connected to that. Everything seems to be pretty tightly connected. Oh, well, let's see. So we trudge on. We'll work on that in a minute or two, and don't worry, lecture is not getting canceled. I don't care how. David?
So there was a question on the homework that said, which of the following substances are Rancid Lowry acid? But they all seem to have hydrogens.
Mm-hmm.
So would it be a case where a molecule is so electronegative that it won't release a hydrogen?
So let me finish this one, and then I'll talk about that. Is that the one? Let me see which one that is.
What's that?
These ones?
Mm-hmm.
Okay. We'll do that one next, and that's a good question to do. All right, so where were we? Oh. This is on your equation and conversion sheet. It's in the Ka table. What I just said before I was so rudely interrupted by a loss of power, or loss of, I guess we have power, we just don't have signal. So anyway, this has a Ka that's on your sheet. It is 1.8 times 10 to the minus fifth. And what you need to be able to do is not only find the Ka for the conjugate, prove that since this is a weak acid Ka, that this is a weak base. All that is necessary. But then you also have to be able to find the Kb for this base. Kb for this base is equal to Kw over Ka for its conjugate. We have Ka for its conjugate from the conversion and equation sheet. What's the value of Kw? 1.0 times 10 to the minus 14. Must know that. Is that on your conversion equation sheet? I don't know, we just use it so often that either we memorize it or we make sure it's on the sheet or not. If we do this, and I've done this one enough to know that it's 5.6 times 10 to the minus 10, and that is in the region of Kb values that are weak bases as well. We said whether you're an acid or a base, to be a weak acid or base, your Ka or Kb value must be between 1 and 10 to the minus 14. In that way, water is like with 10 to the minus 14, it's like it's inert. Water is inert. Water, if you just had water with its 10 to the minus 14 value, water would still have a pH of 7, and that's sort of the definition of inert. As far as acids and bases goes, if you're inert acid or base, you don't affect the pH. With your Kb value, and had I given you an initial concentration, you could set up an ice table around that Kb reaction and tell me the pOH and then the pH. Those are all things you need to do. In particular, the one question that has like 6 things and says, list them from least acidic to most acidic, or lowest pH to highest pH. That is a very common type question on your second exam. And it requires that you be able to look at compounds, break them down, find Ka and Kb values for their parts. Before I tackle yours, David, any questions about this? If not, let me take another question here. Who knows, we might do homework questions the whole time at this rate, although I doubt it. This is number 14 on homework number 3. Although I did say, if I remember correctly, that we did have some time to do homework in class. And so from that standpoint, full steam ahead. It says, this is the multiple choice. Which of the following substances is never a Bronsted-Lowry acid in an aqueous solution? We have sodium dihydrogen phosphate. We have sodium acetate. Ammonium nitrate. Hydrogen bromide, where it then says HCl. Fortunately, the answer works regardless of which one of those that we use as its formula, and sodium bicarbonate. And the question is, which of these is never a Bronsted-Lowry acid? This is related to the type of question we're doing here. You have to be able to look at this, break them up into ions. We have the sodium ion, and I'm just going to cross all of them out. When I cross them out, I have a -1 charge on each of these things that are left. There's one other thing I can cross out as an inert acid or base. Can anybody tell me what that is? Nitrate. Nitrate, NO3 minus. Conjugate acid, HNO3. What kind of acid is nitric acid? It is strong. Therefore, nitrate is inert. And that is another wonderful reason to know your strong acids, because then you know they're inert conjugate bases and you can cross them out immediately. From there, it says what can never be an acid, Bronsted-Lowry acid, and let's see. So HBr or HCl, I apologize for that typo, but either of those can be an acid. So that one could be. So that is not the answer. Could be acids. Well, almost required to be acids, actually. There could be required to be acids. There we go. And then we get to these cases that have H's, but the question is, can they act as acids? Now, I will tell you that whether you know this or not, there are two hints that you can tell acids, things that can be acids from things they can't. One is they will have an H in the front, even if they're a negative ion. So HCO3 minus can be an acid. The other way you can tell is if, and this is again a bit abstract, but it will work. The carbonic acid has a Ka1 and a Ka2. If you know what these stand for, you know that Ka2 is the Ka for bicarbonate. And I encourage you to use those Ka and Kb tables to tell you what is an acid. And if it's an acid and you take away an H+, now you know what can be a base. Same thing up here. There are H's in the front. There is for phosphoric acid, Ka1, Ka2, and Ka3. The meaning of these, by the way, Ka1 is take what you've got for an acid and remove the first proton. That leaves you with this. When you remove the second proton, that's the Ka value for H2PO4 minus. For Ka3, you have HPO4 minus. You're taking the third proton away one step at a time. And that leaves us with this as the only one that can't be an acid, even though it has H's. And the underlying text here, which becomes a lot more important in organic chemistry, is that almost all of the H pluses that we will see are attached to O's. And these hydrogens are attached to a carbon, which means they will not typically act as acids. Things are crazy when they do, and that craziness does not start until O count. Logan?
You showed ammonia as the conjugate acid of ammonia. There's one more, the one below it. Scroll it over.
Sorry, which one are you asking about?
NO3. The ammonia, or the ammonium. Yeah. So that's a conjugate acid of ammonia.
Of ammonia. Yeah, no, so this, we know this is a weak base. That will be a weak acid. Does that answer your question? Or? Yeah. Kate, and then Vivian?
HCO3, and I just thought CO3 was base, that's weak. So that's
Just CO3?
yeah.
Yeah, and so that's, so it's an easy thing to do. The underlying principles here are that all of the ions you will see, or many of them, you've seen before, and so you know their nomenclature. There are no nomenclature tests in this class. However, NH4+, bicarbonate, nitrate, acetate, these are all things that we've seen before. Another hint, and I've seen this a couple times, another hint is these compounds break up into only two parts. There are very rare exceptions where they break up into more, but you should consider that they will break up into two parts, and that something like a chloride is your clue. Since chloride will break up as Cl minus, whatever else is left there must be the plus part, even if you haven't recognized it. And so NH4+, well, that's right there. I don't know. Have we seen this before? Have we not? I don't know, but I've seen chloride before. And so the rest of it. See, I even did the formula wrong. There we go. With a plus. And then your backup is once you create this thing, if this is going to be an acid, look on the KB chart with one less H plus, and you should find the conjugate base. Therefore, you know you can figure out what it is. And you'll have to, because chances are, if this isn't part of the problem, you'll need to know the KB value for its conjugate base. Does that answer your question, Kate? And more so, maybe? I don't know. Vivian?
Can you do another problem with 12?
Number 12. I don't have the homework with me. Number 12 says a certain acid, HA, has a Ka given by blah, blah, blah. A certain acid has a Ka value as Ka equals, now I gave it back.
I went Ka equals 6.80 times 10
Good. And that's for HA. And then it says
what is
you have 0.247 molar well, it says probably K, which is really 0.247 molar K minus. So tricky wording. They gave you a reaction that you don't need, and its Ka value. What you need to circle in on is that you have A minus. A minus, well, if it's the conjugate of HA and it has that Ka value, it will be a weak base. And you need to write a Kb reaction for it and do a Kb iced. Marissa?
So in the notes, we did a similar problem. We found the Ka and the Kb first, and you told us to deal with the one by that was the largest. So in this situation, the Ka was larger than the Kb. So.
Good question. So Ka is bigger than Kb. Do you have a Kb value for this?
1.47 times 10 to the negative 9.
Okay. Now, I see the issue. The problem statement says you have 0.247 molar Ka. The worst possible thing to choose since it's Ka and it's Ka. Potassium anion. You don't have any HA. So that's the reason you can't do a Ka ice table. Although, if you wanted to get really fancy, you could do, I don't even think you couldn't do this. I was going to say, you could try and do a Ka ice table, but you'd only have an initial concentration of your A minus, and things get wackier from there. So you wouldn't have anything to put here, which would mean you wouldn't be able to like, I see where you would go with that, and it would be tempting to put 0.247 molar under that, but I don't know if it makes sense, but you only have the 0.247 molar anion, A minus. I will say that on this homework, does this homework feel long? Yeah, well, I did put everything on it that could possibly ever show up on your exam. I think, your mileage may vary, that homework 4, I was a bit more judicious. Meaning it might be a little shorter. I don't know, we'll see. What I did was I made up homework 4, the one that I'm passing out today, and then I took off about 20%. So at least there's that. Who knows how long. Vivian, does that answer your question, Marissa?
Is that equal to Kb? What if you just have a Kb ice table?
if you have more questions about that, I'm happy to talk about them. We can do it in discussion afterwards, or today or Wednesday, or office hours, tomorrow or Wednesday, or both. So, no, but let's talk about that later.
Okay.
Now, I think that's a good amount of homework time. Let's see if, oh, maybe this is the issue. Hey. There we go, there's one. Let's try that. Oh, I think my computer was dying, and so when I knocked out the plug, it just went to sleep. So, good news, we're back in business. So where were we? Well, we are towards the end of, well, at least the middle, maybe not the end of chapter 17. In chapter 17, we've already talked about buffers. We've already talked a lot about titrations. And what we did was we did, for weak acid, strong base titrations, we did some calculations last time. And one of the places where I left off was for what are called pH titration plots, that as you go from an acid that is a strong acid to weaker and weaker acids that are still weak acids, they're still in that category. I think it says Ka 10 to the minus 2, 4, 6, 8, and 10. The shape of the pH titration curve changes. What we said was that this region, more or less, right there, is what's called the buffer region. But you can see that the buffer region shifts in pH values depending upon the value of Ka. Hopefully that makes sense, because right in the middle, and I guess that'll be a 20, pH equals pKa. Because right in the middle of the buffer region, the weak acid, half of it has been converted to conjugate weak base. Since half of it has been converted, we have equal concentrations of conjugate weak base and weak acid. This will be 1, log of 1 is 0, and pH equals pKa. And when we do the titrations lab, one way to tell or estimate what your pKa is for your acid is to go to the middle of the buffer region. Whatever the pH is, that is your pKa. Any questions about this chart here? I guess the one other thing I'd just like to say, do you have a buffer here? Well, technically you still have a little bit of weak acid and mostly conjugate weak base. I would say you have a largely ineffective buffer. Remember, an effective buffer has between this ratio of conjugate weak base to weak acid between 0.1 and 10. And that's roughly right here. In this little region right here, you've got a slowly or quickly dying buffer, if you will, being exhausted. Up here, you just have strong base. You also have weak base, but as we said last time, if you have a strong base and a weak base, it is the strong base you use to calculate. Logan?
So on the, I guess, lower portion of the graph, the gentleness of that curve is based on if there's a buffer. And then the rapid flip is because you go from having excess
this gentle portion up
Yeah.
here?
Yeah.
Yeah, no, it's akin to this portion down here. You have strong, like if you had a strong acid, it's gonna be just strong acid, which means the pH is very low, just strong acid, so the pH is very, or strong acid and weak acid.
Yeah.
Or no, just strong acid. But up here, pH can't go above 14, so no matter what happens up here, it's gonna be relatively flat. You can see that if you have Ka equals 10 to the minus 2, there's a big, that's very steep. But by the time you get to Ka equals 10 to the minus 10, there's not much more the pH can change. Any other questions? If not, then we just have examples of pH titration plots for other kinds of titrations. We have weak base, strong acid. In this particular case, we're looking at 0.10 molar ammonia with a pH of 11.12. Buffer region coming down. In the buffer region, pH equals pKa. Well, let's say this, right in the middle of the buffer region. Even though the pH is basic, the Henderson-Hasselbalch equation still works. We just have a Ka value over weak acid that is 5.6 times 10 to the minus 10. pK is 9.24, so that's nice. At the equivalence point, you have all weak acid. And therefore the pH is less than 7. And so you're constantly evaluating when you do homework 4 and when you do chapter 17 stuff. What kind of acids do you have? Do you have a weak acid? Do you also have a strong acid? And using them to figure out how to get to pH. Polyprotic, and we'll do a polyprotic titration in the acid titration lab. Those are going to have 2 equivalence points if it's a diprotic. And 2 buffer regions. In the first buffer region, in the center of it, which I guess would be right about there, pH equals pKa1. Let me put the P in there, pKa1. Another buffer region, in the center of this second buffer region, pH equals pKa2. And in lab, what will happen is we'll actually do phosphoric acid. Phosphoric acid is a triprotic. It turns out that the third one has a peak or a Ka3 that is so close to up here that you won't be able to see it. So phosphoric acid will act like a diprotic only because its Ka3 is so high or so small. Its peak Ka3 is so high. Any questions about that? If not, well, we haven't done weak acid, weak base titrations. Always a question, does the reaction go to completion? Well, let's talk about this. So HCN is a weak acid, ammonia is a weak base. we can write what the reaction is, and we'll thank Rachel for this. Now I'm going to call this the hydrogen or proton rainbow, because that's what it looks like to me. So I put my proton on its rainbow. I end up with ammonium and cyanide as my products. Question, does the reaction go to completion? Well, to find that answer, we have to find the Kc for this using available K values that we've already got. For example, we know the Ka for HCN. We know the Kb for ammonia. And we will add reactions up to get an overall reaction just like Hess's law, except that in Hess's law last semester, and good news, Hess's law is coming back again when we get to thermodynamics this semester. So, but for adding reactions and equilibrium constants, what do we do with the equilibrium constants when we add reactions? We multiply them. Good. So I'm going to write out a Ka reaction for HCN. I'll write his Ka value. I know its Ka value because I can look it up on the table. It's 4.9 times 10 to the minus 10. Now I'm going to write out a Kb reaction for ammonia. Remember, I'm trying to create this reaction. I still have a bunch of waters, 2 waters to be precise, and hydronium and hydroxide to cancel out. I want my waters, if they're going to cancel out, to be on the product side. I want my hydronium and hydroxide to be on my reactant side. There's only one reaction that contains all those fun things. So I'll write it out. That is certainly related to Kw, but for it to be Kw, the waters would have to be on the reactant side. So this one is 1 over Kw. So it equals 1 over 1.0 times 10 to the minus 14. And perhaps you remember the feeling of Hess's law and it being a puzzle in which you did not have all the pieces. Well, that's happening again, except that the only puzzle pieces you know are Kas, Kbs, and Kw. And that's it. So those are the puzzle pieces. And the worst thing you can have to do is flip reactants and products. Otherwise. But those are the pieces. All right, so we add them up. We get lots of things to cancel out. And we end up with our reaction right here that we were trying to do. just looking at the numbers, looking at the exponents, we always want to make sure we have an idea whether our math should be correct or not. I have 10 to the minus 15, and then I have 10 to the minus 14 in the denominator, which turns out to be 10 to the plus 14. So 10 to the minus 15, 10 to the plus 14, our number is going to be somewhere around 1. Within, you know, if you actually calculate it, we'll call it KC1. It is an equilibrium constant in terms of concentration, so it's a KC. It works out to be 0.88. Now, does the reaction go to completion? It does not. Not with a value of 0.88. It goes about halfway. And one of the things we haven't talked about too much so far is, okay, if we're going to do a titration, the only reason to do a titration, pretty much the only reason, is if the reaction goes to completion and you can figure out the concentration of the unknown acid or the concentration of the unknown base. So to finish this up, reaction does not go to completion, so we will not do it for a titration. Reaction doesn't go to completion, not good for titrations. Period, the end. Question?
So, do we do anything with our Ka, Kb value, or?
Do we do anything with our Ka, Kb value? So I skipped something here. So Kc1 that I calculated right here is Ka times Kb times 1 over
Okay.
Kw.
Okay.
That's where I got that 0.88 from. So yes, we do need it. Any other questions? David?
So Kc is related to Kw. On the homework, I believe there was a
This
question
one
that
is?
asked if what is Kc, and it gives you a Ka value, but doesn't give you a Kb value. So could you solve it through using 1 over Kw?
So, question about the homework. It's asking for, I believe, a Kc for some reaction. And I would say there are very few things that we can do. This is one of them. If you find the problem, we can talk about it. But the only other thing we can do, as far as I know, and I apologize, this is probably going to be a companion problem anyway, but I'll write here for a minute. So, I don't know what the problem is you're talking about, but this might be a good example. So the question could be, write the products and tell me the K value for this. Now, that's going to be your base, right? That's going to be your acid. I love this so much, by the way. Here comes another rainbow. Has to be that way, right? That means that we're going to have H2O. And cyanide, Cn minus. And the question is, what is the K value for that? Does anybody know how to find it? What's that?
1 over Kb.
It's 1 over Kb. Your process was probably this. Here's water. Water always appears on the reactant side if it's a Ka or Kb reaction. And whatever's next to it determines whether it's a Ka or a Kb. So since this is a base, this is going to be a Kb. Because they're on the product side, it's a 1 over Kb. So I don't know the exact question. We'll have to talk about it afterwards, David. But But there's only Kas, Kbs, the reverses of them, and Kws. And while it seems like there's a bazillion alternatives, it's just, it's combinations thereof. And it has been my delight to work through a bunch of problems with people in office hours and in discussion and watch their process. And it is a process to feel comfortable with all these things. So I encourage you to all talk to me. I've seen lots of study groups. Oh, I should say this, by the way, about study groups. If you're in a study group and you want extra credit, and you have not turned in a log of your meetings so far, I asked for that at exam 1. I will take it up until this Wednesday. And after that, I'm going to assume there are no more study groups that want extra credit. So just get it to me by Wednesday in a hard copy form. Marissa?
Why exactly do the reactions need to go to completion to be good for titration?
Good question. Why do they need to go to completion to be good for titrations? Well, I mean, the short answer is that oftentimes titrations are used to determine the concentration of an unknown acid or base. You cannot, and that if you want to do that and have a nice equivalence point, have a nice titration plot, the reaction has to go to completion. Otherwise, you've got, I mean, think about what you got here. If you've got 0.88, you've got a weak acid, a weak base, another weak base, and another weak acid at equilibrium with appreciable concentrations. And so I guess the slightly longer answer is it just gets super messy if the reaction doesn't go to completion. And super messy to a chemist is not generally useful. I mean, especially in 400, Chem 400 and 401. I'm trying to think.
Is this like a case where we would like to make like a primary standard?
So is this a case where we would make a primary standard? I would say for titrations, yes. And yes, and only for good ones. I would say the one other thing about this problem is that while we would never do this as a titration, I could ask you to tell me what the K value was for this. And so the real reason, if your question is why, if this is not a good titration, are we even doing this? It is because it's a very nice demonstration of how to add reactions and find a Kc value that you don't know. Logan?
If the products in this reaction were not aqueous, they were solid, precipitated, or gas evolved, would that change whether it goes to completion or the amount that it goes?
Good question. If these were solids or gases, would that change whether it goes to completion or not? The extremely short answer is they never will in this portion of the class because this is all acids and bases. The longer answer is we are about to deal with solids and what happened, and even, to go off on a tangent a little bit more, we are still going through a very limited set of reactions that we can analyze. And we're trying to make them as interesting as possible because acids and bases are interesting, especially, they're interesting to chemists, they're interesting to biologists. Because they have, many types of reactions like this have sort of either direct analogs or analogies to bodily functions and pHs and things like that. But another long answer would be, if the phases change, of course everything changes. And we just couldn't do it. All right, well, on to acid-base indicators. We don't spend a lot of time on acid-base indicators. There's more material in your textbook about it if you are interested. The one little bit that we are going to do is this little animation and talk about phenolphthalein. Phenolphthalein is one of the indicators we used last semester. It is one of the indicators that we will use this semester as well. And what we know about indicators is they tell us where the end point is, and the end point is when it changes color. And I just wanted to say a couple words about the fact that most acid-base indicators are weak. Does it say acids on your paper? Or is it covered up, like on my overhead? It's covered up. Oh, well. It says acids under there, believe me. You'll have to. Anyway, and so while phenolphthalein and this animation I found online shows that it is a complex process, how it goes from the acid solution in which it's colorless to the basic solution in which it's pink. It is due to the fact that there are weak acids that are changing into conjugate weak bases as this process goes. And we only add 2 or 3 drops of indicator to the solution. It is not the dominant acid in the solution or the conjugate weak base, and it goes along for the ride and responds to the pH, say, of a buffer or an equivalence point or a strong base. So that's all I wanted to say, and we will not focus on indicators, but I wanted to point out that they are weak acids. And so in my nomenclature, those are parentheses that tell you, while this is very interesting, it will not be on the exam. Like I said, we're going through a very specific set of equilibria that we can deal with. Now we're going to talk about solubility equilibria and the equilibrium constant. These are going to be dissolving solids in water. And the first thing I'm going to tell you is that solubility product and the things we are now talking about, in Chem 400, they were considered insoluble. And now we will find out that they will be slightly soluble, and that's why we're interested in them. For example, silver chloride. Last semester, my favorite example of something that was insoluble. Now, one of my favorite examples of things that are slightly soluble, and we will start by calculating it. These are still dissolving reactions, and so these are the same reactions we did last semester. When you write them, they go like this. Take whatever it is that's a solid and make it aqueous, since this is an ionic compound. The products are ions. And last semester, if you remember way back to the beginning when we talked about strong electrolytes, weak electrolytes, and non-electrolytes, my definition of a strong electrolyte or weak or non-electrolyte, you had to dissolve. So we didn't even consider this. We just said silver chloride insoluble, forget about it until now. Okay? But that's all it is. They're all dissolving reactions. And for solubility products, they will all be ionic compounds. Now, if I was to ask you to write a KC for this, you would say products over reactants. The reactant is a solid, so it doesn't show up. And that's exactly what we're going to do here. Yes? And instead of calling it KC, I'm going to call it KSP, but it follows all the same rules as KC. But since it's a named type of reaction, it has a SP. SP stands for solubility product. And now I have to add my chloride. And the solubility product constants, the KSPs, are tabulated on your conversion equation sheet, so you have them. If you look there, you will find 1.77. Times 10 to the minus 10. That small number indicates that this reaction does not go very far. And that is in line with what we learned in Chem 400, which is this is we called it insoluble. It is almost entirely insoluble. We can do the same thing for dissolving of iron 3 oxide. Write the reaction. This time we get 3 hydroxides and KSP. As the hydroxide term cubed. Nothing new there, just want to make sure that we don't forget our cubes when we have non-1 coefficients, since it's been a little while since we had a non-1 coefficient. Questions about this? Question, yeah?
Why is it useful for us to know that it breaks up just that small amount? Like, what does it attribute to?
Great question. Why is it useful to know that it breaks up that small amount? The thing that immediately jumps to my mind is drinking water. So and we haven't talked about lead, but lead's coming up. But if you have things in your drinking water that will be even slightly soluble, you will taste it, and or it can kill you. So, right? So you hope, and I mean, so what happened in Flint? They changed the pH and the amount of ions in the water, which changed the solubility of lead and greatly increased it. And so, I mean, it's a terrible situation. It was, and last I heard, it still wasn't that good. They were still drinking bottled water in all the places.
That's pretty useful.
So that's at least one reason. Let me see if I flip through here. So, medical reasons. Has anybody ever had or known anybody who had a scan of their gut? You have to drink a solution of barium sulfate, which is highly insoluble depending upon pH. But barium is toxic and so there are issues, right? There are things you want to know how soluble something is, say, in your blood, in water, and anyway, so you may or may not ever actually encounter these examples, but somebody's thinking for sure about what's soluble in your water right now. Yeah. So, and actually there's this, I mean, to be honest, there's a lot of jobs, a lot of state jobs in being able to know the chemistry of water, especially as water levels change and water chemistry changes in response to the aquifer changes. It's a huge issue. Anyway, I hope that starts to address it. Okay, so now we've done some KSPs. Now we're going to calculate what's called the solubility limit. We're going to do it for lead chloride. Lead chloride has a KSP of 1.17 times 10 to the minus 5th. There you go. More ice tables. This time we'll set up an ice table in terms of molarity with a KSP reaction. What's a tiny bit different about this one is that underneath the solid, I am going to write question mark and minus x for the change. Question mark is because, you know, it's not a philosophy class, but if it were, we might say, what is the meaning of the concentration of a solid? And that's what the question mark means. But what will be important is this x, and that's what that minus x, and that's why it's there. Because that minus x is the solubility. It talks about how much of it does react away. We've seen minus x's under solids before when we talked about ammonium chloride and how much dissolved. We start with 0 dissolved for the ions. We still carry our coefficients into our plus 2x area for our change in concentration. Very easy to forget one of those 2's. The coefficient shows up both in the 2x part and the squared part. And I have to double, yeah. But the lovely thing about this, no denominator, no quadratic equation. Our KSP value turns out equals 4x cubed. Divide by 4, take the cube root to solve for x. X is the solubility of the lead chloride. The solubility is whatever goes here. The solubility is 0.0143 molar. It is also the concentration of lead ions. Double it, and you'll get the concentration of chloride ions. I did that chloride math in my head, so you should be impressed. Now, thank you. Now this is, so you will see problems like this that will then give you a volume of solution. If you had a volume of solution and a molarity, you could then work back to how many grams actually dissolved. I think we're saving that for future problems right now. Any questions about the calculating the solubility? Then we shall continue. Now, chemists, if anything, are control freaks. They say, well, that's the solubility, but I don't want to just know the solubility. I want to control the solubility. The common ion effect is one way to do that. What is the solubility of lead chloride in a solution that already has chloride ions in it? I guess I'm going to move that one back so it's actually on the correct one here. There we go. One more. There you go. Good. Because what I want to show you is what is the effect on the solubility when we add this. Now I'm going to set up a KSP ice table. And if your question, I get this, if your question is, given this type of problem and given a KSP, how do you know, how do you know what kind of ice table to set up? You're on the right track. That is the big question in this entire set part of the class. And that's why you're doing 100 or so, lots of problems. But in this particular case, I will tell you, if I give you a K in a problem, you're going to use it, and you're going to use it for this of some sort. Same ice table, same question mark, but now we have a concentration of chloride. Our concentration of chloride ions, well, we have 0.100 molar sodium chloride. That means we have 0.100 molar chloride ions. Sodium, again, a spectator. Chloride, usually a spectator, but this time it's important. Your ice table knowledge definitely helps you because you still see that 0 there. You still know the reaction must go to the right. Plus 2x, thank you. Plus 2x. And now we're going to plug in the same kind of thing, except we have a different term for chloride. Uh-oh, quadratic. I sure do not want to solve that quadratic. How about you? Let's assume that we can ignore that, and then we'll check it in the end. It is true, by the way, that since we have some of this product here, that the reaction will go a lot less. So it will hopefully be a good assumption. Then x equals 1.17 times 10 to the minus third? Wait a minute. Divided by right, so we're going to have 0.1 in the denominator, so it's going to make it 1.17 times 10 to the minus third, which is what you get right there. And that is our solubility. It is also our concentration of lead ions, concentration of chloride, and the last thing we're going to do, I'm sort of out of space, maybe you have some space down there. I'm going to do it up top here. I'm going to calculate the ratio of solubility in pure water divided by solubility in 0.100 molar chloride ions. We get a ratio of 12. That means in pure water it is 12 times more soluble. Another way of saying that is we have just changed or decreased the solubility by a factor of 12 to get here. And we have changed, and I would say, depending upon the concentration of chloride ions, we can control the concentration, or we can control the solubility. Question?
Yeah. Where'd you get that? Are we using the value that we got from the last problem?
Yes, we're using the value we got from the last problem for the solubility right here. Divided by the value we got for the solubility right here. And showing that we have changed that solubility by a factor of 12. We have decreased it. So this is being the smaller number.
Okay, so it's the solubility of pure water divided by solubility. Okay.
Yeah, and just to be clear, and maybe I'm not, is the solubility of lead chloride in pure water and the solubility of lead chloride. Like, it's the lead chloride that's soluble.
What is the factor of 12 indicating?
What is the factor of 12 indicating? Good question. It is saying that by moving from pure water to 0.1 molar sodium chloride, we've changed. So the difference or the change is a change. It is 12 times more soluble here. That's not the good answer, though. So chemists are all about control, right? They want to know what they did. I added sodium chloride, and I decreased the solubility of lead chloride 12 times. I still don't like the wording of that. The solubility of lead chloride by a factor of 12. It is 12 times less soluble. So PbCl2 is 12 times less soluble. It's not an English class, but I feel good about that statement, like that's how I want to say it. I controlled the solubility and decreased it by a factor of 12. Right? Because really what I don't want is I don't want to know how much more soluble it is here. I want to know how much less soluble it is here. If that makes any sense, but that's what I did. Yeah.
So, could we rely on the knowledge that we're dissolving an insoluble compound? So we could always count on ignoring that X, because we'll know that it's still going to dissolve, or at least go less than 5% all the way?
So, yeah, so can you ignore X? The short answer is yes. This value of KSP is about the largest there is, meaning that if your KSP is bigger than this, you're just considered soluble, and we wouldn't do this problem.
Okay.
So you may ignore X generally. I'll finesse that. Does that answer your question? Yep. Without saying anything else? All right, so now that's the solubility. That's us controlling the pH, or sorry, the concentration, solubility. Now let's talk about the effective pH on solubility. And we'll have qualitative first. That means without numbers. How would the solubility of magnesium hydroxide solids change at high pH versus low pH? Let me write out the solubility reaction for magnesium hydroxide. It's just going to be magnesium hydroxide dissolving. When something's at high pH, we can think of that as being equivalent to adding hydroxides. Does that make sense? When we add hydroxides, what does Le Chatelier's principle tell us will happen? It will shift to the left, And what can we say about the solubility of magnesium hydroxide? It will decrease. So our thought process is high pH has more hydroxides. Le Chatelier's principle tells us that this reaction will shift left. Shifting left decreases the solubility. I always like to imagine that Le Chat is French for the cat. I don't know if that's true or not.
It is.
I probably heard it at some point, but I then forgot it.
So, can you explain, so decreasing the solubility of the magnesium hydroxide because it's just adding more, more solid? I don't know.
Ah, what is, so for this part, so let's assume we're in pH 7, we only have pure water. We've been using that term pure water a couple times already, right? And pure water functionally means pH 7, for one thing, and nothing else. Like pure water did not have any of these chloride ions in it. It was just water. And so the other thing that means is that the only reaction that can be happening is the KSP, right? And still the only reaction here is the KSP reaction, but now we have something to put on product side. And what happens? When we had something to put on the product side, the reaction actually shifted to the left. That's the same thing we're doing here without numbers, well, without numbers yet. If we allowed this reaction to get to equilibrium in pure water, then it would go whatever it was going to go. And then we can imagine if it's at equilibrium and then we add hydroxides, it's going to shift and take some of that away, which will make that X term smaller, which means, and since X is our solubility. We'll do it with numbers shortly, but for this type of thing, you want to, or I want you to be able to do it qualitatively like this, and then quantitatively as well. The nice thing about quantitatively, by the way, is that if you ever get in a jam, just make up an ice table, and you could plug in numbers. You could be like, well, okay, you know, how much time you got on your hands? Well, if you had an extra half hour during the exam, so, okay. But you can imagine, and this is a technique I use quite often now. Not for this scale problem, but if I don't know what's going to happen, I will make up numbers and then see how the problem reacts. This would be, I guess my point is, this is a bit more than you would probably want to do to solve an ice table, but you could say, okay, look up the KSP, find the solubility, then have an initial concentration of hydroxide, solve for the solubility again, you would find that it has shifted, so your solubility would be less. So it's totally possible to do, maybe there's not enough time. But as a thing to do to get more points on exams, plugging in numbers, even if it doesn't ask for them, can sometimes help. Does that answer your question or address it?
Yeah, a little bit. I think also it's kind of confused with the previous example you said that we're given the molarity of NaCl, so we start with our products, and then you said that the reaction shifts to the left. With that example, how do we know?
Good, okay. So, I erased it now, but there was an example over here where there was a 0 here, right? And I solved it, and I said that the concentration here was 0.0143. And when I did that, there were zeros here, and I went to the right. And then for this problem, I went back to the beginning of the reaction, didn't I? Because then I went to the right again. And what I could have done is I could have started with my equilibrium values from the last problem, then I would have gone to the left. But had I done that, I would have had to solve a quadratic. Because if this reaction goes to the left, and it has a small value, I don't know, in the end you have to solve the quadratic. For reasons we can talk about if you want. But that's why I just went back, so it is always easier if you can to go with a small k value to go to the right. Then you can make this assumption. But I hear you, V, it's like, we're awash at C because we're always shifting left, shifting right. How do we know where to start a nice table? And in the -1 minutes that I have left, I will say, hang in there. The people who are putting in the time, and it takes a lot of time, and I know most of you are going to get there. You're going to get to the point by the second exam where you say, I can look at this ice table and generally know how to approach it. If not perfectly. So hang in there. That's all I have for today. That's it.